Hello, and welcome to Lecture 8 of AMAT502 at UAlbany. Today we're going to be discussing more of object-oriented programming and looking at some fundamental data structures which are common knowledge among computer scientists. We'll look at how to implement one of them using the notions of object-oriented programming. So it's important to be familiar with just the broad concepts of object-oriented programming. In broad strokes, you want to think of object-oriented programming as a system for thinking, where you treat things as objects and types, which are to be defined, along with a set of operations that you can perform on them. Many important concepts of computer science are wrapped up in the notions of object-oriented programming. So it's something that deserves much more time than we're going to give it in this course. Make sure that by the end of this course, you at least can be able to speak broadly and intelligently on some of the terms that are used in this diagram, such as the notion of an object, a class, a method. All of these are things which we introduced last lecture, along with attribute. Some of the things we'll get to today are the notion of a polymorphism, sometimes called method overriding, and inheritance. Encapsulation is referring to how to reserve or make certain attributes private. And abstraction is a concept we touched on in earlier lectures, which also really comes to play in object-oriented programming. So I encourage you to study this diagram and understand the meanings of the words that are used in it. All right, so let's do a quick recap. Last lecture, we introduced this notion of the car class. These are meant to give us a way of representing the notion of an object which has the properties of a car. Namely, it has a year, a make, a model, a color, and maybe there's some things you want to do with it, like make it go and make it go a certain speed. Let's go ahead and see how we defined it last time. So we always want to, instead of using the word DEF, use the word class. So here we're going to make a car class, and we have to initialize our object by using this init method, where we have double underscores on both sides. Some of the attributes which you have to pass when creating an instance of the class car is a make, a model, a color, and a year. Remember, you don't need to actually pass the argument for self, because that's specified using the variable name that you set your car equal to. Anyways, we also initiated some other attributes, such as its speed, which we set to 0, and we assumed our car was given to us off. We then specified some methods, such as how to start our car and how to turn off our car, all of which just changed the Boolean value of whether or not my car, which is going to be represented in its instance using the keyword self, whether self.on was equal to true or whether it was equal to false. So I really hoped you enjoyed some of the programming exercises we did in class last time. It's important to think that really the sky's the limit when it comes to what you can do with object-oriented programming. And you should sort of think of it as a text-based game. You specify some of the actions you can do, you all enter them in the little text box, which then have consequences as specified by the rules of your class. I want you to really imagine you could create an exotic universe in object-oriented programming, perhaps populated with objects like Shabraz the sky shark, something which is known in Magic the Gathering. But the commonalities are that whatever the sky shark object is, it has various attributes, such as things it can be partnered with, and certain strengths, and ways in which it interacts when other cards are played. So object-oriented programming really lends itself ideally to the sort of framework of thinking about text-based games and other sort of card-based games. All right, so we're not going to have any sky sharks in our class today, unfortunately, but we will go ahead and try to make our car a little more interesting. All right, so here we've got the same initialized method that we had previously. And I haven't changed anything about how we start or turn off our car. But I've now added two more methods that I can perform on any car object. I can tell it to go faster, which I first ask, is my car on? And if it is, then I add 10 to it, whatever the speed is. I'm assuming that we're working with miles per hour here. And in case it's not on, I'm just going to say, you can't make the car go faster. The car is not on. Similarly, we have go slower, which decreases our speed by 10. And we can stop, which sets our speed to 0. And then finally, perhaps we're just interested in monitoring our speed to make sure that we're not speeding. In which case, the method check speed would be useful. And it provides a string as the output, which tells you what your speed is viewed as a string. Let's go ahead and bring this new definition of the car class into memory. Okay, so let's start with, let me call this my old car. Just make it different from cars, which I'll create later. My old car is going to be a Chrysler minivan from 1995. All right, not very exciting, but here I can go around and first start my old car, and then I can make it go faster. And then I can also check its speed. So let's see what happens when I invoke these three methods: start, go faster, and check speed. All right, well, first of all, let's see what happens if we just call the first method, meaning start. It doesn't return anything. That's because this method doesn't return anything. If you look back at the code, all it did was modify the state of my on attribute, switch the value from false to true. So it doesn't actually output anything. Neither does go faster. And of course, if I happen to run this without first starting it, well, it actually still works because it remembers when I've modified its attribute last time. So kind of defeats my point. But let's suppose I do it this way. I'm going to first create my old car, and then I'm just going to ask it to go faster. That'll tell me the car is not on. All right. So first I start it, and then I make it go faster. Again, no output because these are just modifying the attributes of my old car object. But I can now check the speed. Checking the speed returns a string, which says my speed is 20 miles per hour because I ran my go faster method at least twice in the cycle of hitting shift enter. Now let's make sure I can stop it. So let me stop my old car. And again, there's no output. But let's go ahead and check speed. My speed is 0 miles per hour. And then finally, I've turned off my car. And again, the way a Python cell works, if I ask for a variable and I make that the last thing entered into a code cell, it'll go ahead and try to evaluate it, and it'll print its value to the screen. So when I ask, is my old car on? What I'm asking is, what is the value of that attribute, my old car.on, which because I turned it off is now off, which is represented using the Boolean value false. Okay. So here's some more methods which we can introduce. We've already introduced the init method, but there are at least these two others which are special and go beyond just crazy operations I might want to perform, like go faster and such. And you know that these are important because they're surrounded by these double underscores. And so I have str with double underscore on both sides, meaning there's 2 underscores, and then lt with 2 underscores on either side. So these have something to tell you about what other parts of Python can access and use these methods. Specifically, what the string method does, the one where I've separated it by 2, or encapsulated it with these double underscores, this is essentially telling Python what to do if I try to print my old car. And additionally, I can also ask, well, what happens when I do my less than operator, LT, that's less than, it tells me what happens if I try to compare two objects of the car class. So we've already sort of understood there are issues where the less than operator can be used even for things that aren't numbers. So for example, if I wanted to do is A less than B, well, that's true if we use this notion of alphabetical ordering. Or more broadly, if I use like ABC, is that less than ABD? Yes, it is, because it compares character by character and then looks for the first place where there's a difference and then just use the normal dictionary ordering on letters or alphabetical lettering on letters in order to specify the value less than. So essentially what I'm saying here is that using str and lt inside of a class definition, we can specify how Python should print and how it should compare these types of objects. So in particular, if I have, when I go back now to instead of making this my old car, I'm gonna make my car equal to some car that is a Jeep Cherokee that is green and from 2000. I now can make sense of what it means to compare, say, my car, my Jeep Cherokee, with whatever Jordan's car is going to be, which we'll specify soon. All right, so let's go ahead and introduce some of these more sophisticated methods. We've already have our initialize method here. It's completely unchanged. But now we're going to introduce str and lt. Again, this LT stands for less than, and it allows comparison. So I'm going to come up with the following way of printing any car object. I'm going to return the string, this car is a, and I'm going to specify the color, the year, the make, and a few other operations which just indicate that it goes color, year, make, model. We'll see how that prints very shortly. For my comparison operator, I'm going to do things slightly differently. I'm going to first focus on their speed. So if I have two car objects and I ask, is one less than the other? What I'm going to ask is one going slower than the other? Now, in the off chance that their speeds are equal, I'm going to return whatever the comparison of their years is. So older cars built in earlier years are considered less than or equal to older cars built in more recent years. So I've been able to make sense of what it means to compare two car objects by specifying what happens in this LT method. But notice I need two arguments, self and other. For other is going to be however else I'm going to, whatever object I'm comparing to. All right, the rest of these methods are still the same. Start, turn off, go faster, go slower, stop, and check speed. All right, so let's play around with these. All right, so I've gone back to my Chrysler minivan. I'm not so happy with that. Let me go ahead and make this a Jeep Cherokee that's green and built in the year 2000. Jordan has a much nicer car. It's a white Mazda Miata built in 2018. So let's go ahead and figure out what happens when I print each of these things. Now, normally print as a function in Python knows what to do with strings. And then if I give a comma and I give another variable, it's going to do its very best to try to turn this into a string or something that's printable. Notice I just have the instance of my car, which is a Jeep Cherokee. And so I'm just going to ask when I execute this code cell, what happens when I print Jordan's car? Of course, I've added this preface. When I print Jordan's car, I get whatever happens when I specify Jordan's car. or print Jordan's car. And then I also have the statement that my car is less than Jordan's car is, and I'm going to see what happens when I compare them. And then I'm going to try to make my car to go a little bit faster to see if I can be better than Jordan's car. All right, so making sure I brought this into memory. Let's go ahead and execute this code cell. All right, so here's our output. When I print my car, I get this car is a green 2000 Jeep Cherokee. And when I print Jordan's car, I get this car is a white 2018 Mazda Miata. And then the statement that my car is less than Jordan's car is true. But once I start it and make it go faster, based on the logic of how I compare car objects, I now can say that actually my car is better than Jordan's car, or greater than. In particular, the statement my car is less than Jordan's car is false. And just to make sure that we're all on board here, let's see what happens when I just do print my car. All right, so we now understand the logic behind modifying the str method and the lt method inside of a class. So let's focus on the next two important concepts from our object-oriented programming circle. These are the notions of inheritance or overriding. Overriding sometimes gets conflated with the term polymorphism. I prefer to use the term overriding. So specifying or bringing us back to our example, we all know that not all cars are created equal. Some go much faster naturally than others. So how do we capture this behavior or this phenomenon? Well, one way of doing it is to specify a new special type of car, which I'll call a sports car, which allows me to go faster than an ordinary car. When I make this new subclass or subtype of a car, I inherit all the methods and attributes from its parent class. So in general, there's this notion of classes sitting inside one another. You have a superclass that has inside of it subclasses and so on. In fact, in all of Python, all classes are subclasses of the superclass object, because everything at runtime in Python is an object. So the syntax for specifying a subclass means whatever I want my new class, my new subclass to be called, I then put in parentheses whatever class I'm trying to borrow methods and attributes from. So in particular, in the example I just mentioned, if I want to create a sports car subclass, I can say class sports car, but then if I put car in parentheses, I know to inherit all the methods and attributes from the car class we just wrote. Some of you might like mathematical notation, and I encourage that. In particular, you should think of sports cars as a subset of cars. That's what this symbol here means. Or just said in English, it's the logical statement that every sports car is a car in particular. And I just want to note that the code class sports car parentheses car is really going to have some important effects. It's going to allow all sports cars to have access to whatever methods and attributes were specified in the parent class car, unless I've done some sort of encapsulation to hide certain attributes. But we're not going to focus on that in today's lecture. All right. But let's focus on another setting. Namely, suppose I write a subclass, sports car, and I want to still use the same language, go faster. But for go faster for sports car is going to mean something that's a lot different than go faster for a regular car. Let's see how I should do that. All right, so I have my class sports car, which is a subclass of car. I don't need to completely rewrite the init method. So in fact, when I go ahead and specify the init method, I can just call car.init with all of these same arguments that were specified here. So what this does is it has the effect of going ahead and initializing my sports car as a car object. If I wanted to bring in some extra attributes, I could do that in my init method here. But for now, nothing's different fundamentally about a sports car and a car when it comes to its status of being on, off, and what's its make, model, or year. Okay, so now here is where we're going to override the go faster method from car. So just like before, I'm going to check that my car is on. And so I still use the syntax self.on, and I ask if that is equal to true. Technically, I don't need to write this, but it's easy to understand that way. If my self.on is true, then whenever I go faster, I'm going to increase the speed by 50 miles per hour. And similarly, when I go slower, I want to balance that out. So I'm going to go minus 50 from whatever my current speed is. I'm also going to add, a fun method which doesn't override any method, but is unique to the class of sports car, which is I want to do a wheelie, go so fast that I'm up on the back wheels of my car, which is just going to return the string, rad wheelie, man. All right, let's see this in action. Again, bringing this code cell into memory. All right, so I had my old car, I had my car. One was an old minivan, one was a pretty old Jeep Cherokee. But now I've decided I need to one-up Jordan. I need to have my own sports car. So what is my sports car? My sports car is equal to sports car. That's my subclass name. And I specify all the same arguments I did earlier. My make, my model, my color, and my year. All right, so here I'm going to start it, go faster, and check speed. And let's see what happens when I execute this code cell. So just by going faster once, I was already able to increase my speed by 50 miles per hour. So let's see. I'm assuming it still has in memory what my sports car is. So let me see what happens if I go ahead and run this one more time, and another time, and another time. I'm now going 200 miles per hour. It's time to really make things fascinating here. And I'm going to do a wheelie. Rad wheelie, man. All right. Well, remember, I did have another car, which I called my car. What happens when I print my car? My car is a green 2000 Jeep Cherokee. Let's see if my Jeep Cherokee can do a wheelie. No, it cannot. And Python says exactly what's wrong. It returns an attribute error. And it says, car object has no attribute, do wheelie. So again, the code cells in these Jupyter notebooks are very good at telling you interactively what's wrong with your code. Learn to read them well, and you should be able to debug any code you write. All right. So this basically wraps up everything I want to say about object-oriented programming. This is not meant to supplement or replace a proper computer science education. I'm just trying to make sure everyone has some notions that are really principled in computer science, and which will allow us to sort of understand syntactically what happens when we go into these other libraries and packages in Python, like NumPy. In particular, using the dot notation implicit in those libraries only really makes sense if you understand this broader structure of object-oriented programming. And I'm hoping that you now are gaining greater appreciation for what is happening under the hood in Python. Meaning, when we were just starting on our first day, we already introduced these comparison operators. And we knew what would happen if we tried to say 23 less than 42. First of all, we know that makes sense as humans because we understand what it means for one number to be smaller or larger than another. And in particular, in this case, we know that that comparison operator is going to return true because 23 is less than 42. Moreover, Python, if we tried, would go ahead and know what to do if I asked to compare the string cat and cactus and ask, is cat less than cactus? Well, it's not less than cactus. And that's because cactus is actually less than a cat. because C and A both agree, but T is later in the alphabet than C. So in the lexicographical ordering, cactus actually precedes cat. So we're already now understanding that even when we looked at objects of string type, string is really a class. And these, when I go to print a string or I go to compare a string, meaning deep down in Python, there is an LT method which explains how to compare two strings. It went through the notion of lexicographical ordering. There are many other instances of this. So for example, the length function. The length function knows how to be applied to various objects of various types. So if I ask for the length of a string or the length of a list, it knows to return a number. All of this sometimes goes underneath the heading of polymorphism. Polymorphism just means it has many forms or many expressions, and essentially gives you the ability to use the same code to do really different things. I encourage you to go ahead and complete our little circle of object-oriented programming by looking up what encapsulation is. We're not going to have any need for it in this class, but it would be useful for you in your future studies. And I provide a link to an article that tries to understand what encapsulation in Python looks like. All right, so we're now on to the second part of today's lecture. And these are the broader discussion of data types and structures. And additionally, this is a good setup for some of our live coding exercises that we're going to do in class, where we're going to investigate the notion of a stack and a queue. But as a quick summary, I want to mention that part of the reason we go over these object-oriented programs, again, we're trying to understand what's happening under the hood in Python. And in particular, we're trying to understand maybe some of these other data types that we've encountered so far. We've already alluded to how a dictionary is in some sense really a pair of lists. It's a list of keys and a list of values. You could reasonably try to code up a class of dictionary where you use some of these more primitive data types of lists to try to manipulate and work with dictionaries. As I already mentioned, we can create our own data types in Python just by doing things like creating car objects or even creating special types of sets that can only operate in certain ways. Closely related to the notion of a data type is the notion of a data structure. Now, I'm not a computer scientist, but my general understanding of data structures is that this is sort of a more theoretical concept for how you might want to store, represent, or access data. Generally speaking, a data structure is something you could write down in a textbook, but if you actually wanted to implement a data structure in a particular language, you'd have to get down to concrete implementation details and see how do you use some of the existing built-in data types like lists or strings in order to make your data structure work. Broadly, I say a data structure is a prescription of how to structure your data. All right, that sounds pretty circular, but it does actually get closer to the notion of if you have a particular problem and you're trying to do a particular thing, you might ask yourself, if I were to try to represent this formally, how would I do it? And what would be the basic operations I'd want to perform on my data in order to accomplish my task? Generally speaking, though, whenever we go to implement a particular data structure, we're going to use multiple data types. This leads to the analogy, data types are atoms, as data structures are to molecules. So in that sense, people like to say that data structures are more complicated than molecules. I take data structures more complicated than data types. I take issue with some of that because, in fact, some of the data structures we're going to look at now are sort of even simpler in spirit than some of the data types that we already have built into Python. So let's just look at some of these examples of data structures. The two we're going to be looking at today are called stacks and queues. These are sort of fundamental objects in the study of theoretical computer science. There are also things like hash tables, which essentially provide good, quick ways of looking up things. Linked lists, binary trees. These are meant to be data structures which deal very well with tree-like structures. And also, I bring in an example from one of my favorite fields of algebraic topology, where I look at simplicial complexes, which sort of involves grouping together sets of vertices in very specified ways. And there are certain operations you can perform on simplicial complexes, which makes it feel almost like a data type or even a data structure. Bottom line is, I feel like the distinction between these two notions, can be a little bit blurry. But let's get into the particular examples of stacks and queues now. So broadly speaking, we want to think of a stack as a more dynamic version of a list. But we're going to actually implement it using the list data type. However, just as a recap, remember, lists are actually pretty useful data structures, or I should say data types. In particular, imagine we're shopping with a list for groceries, where we've just sort of added elements in when we want to go, where we want to go in the store, and what do we need to purchase there. We can add elements on the list anywhere, maybe squeeze in between two lines, maybe just at the end. And as we move through the grocery store and buy things, we can cross them off in whatever order we managed to buy them, which just corresponds to the fact that we can actually remove entries midway through or add them at the end. And items are going to be re-indexed relative to where we removed our items. A stack, by contrast, is more rigid than a list. In particular, the way in which we insert items and remove them is pre-specified in a very, very rigid manner. In particular, you want to think of a stack literally as a stack of books, where you don't want to just try to pull a book out from the middle of the stack. It's very hard because you've got a whole another pile of books on top of where you are in that stack. Instead, you're going to put things on top and then remove them. So we say we will push an item onto a stack, or we'll pop it off the stack. So stacks are sometimes said to be implemented with this last in, first out. So meaning if I have, say, a stack of papers that I want to look at, then if I need to pick up a paper, I can only pick up the paper that's on the top of the stack, which meant it had to be the last paper I put on there. There are some examples of how we can do things like viewing a string as a stack. And we might want to ask how we could reverse a string by using this order. We were able to do that by popping off the end of the string and putting that onto a new stack, and then just going through and popping off each item of the string on top of the new stack. And that new stack will now contain our string in reversed order. So here's a quick pictured summary of the difference between stacks and queues. So here we have our stack of objects. We push, that means we put something there. It's now on the top of our stack. And then we can also pop. So this is an example of its last in, and then it's also going to be the first out. By contrast, a queue is like a line. In fact, in Britain and other British English-speaking countries, they don't talk about waiting in line to go to the Apple store. No, you wait in the queue, or you queue up. And we all expect the queue to operate in this following way. Go to the back of the line, and you're going to be the last one to be served if you're the last one in line. So in particular, if you're the first to be in the line, then you're going to be the first to be out. So queues have this sort of first in, first out, rather than last in, last out, where we think of first and last being ordered dynamically, meaning at what point did you arrive, and at what point are you going to be removed from either a stack or a queue. All right, so let's see how we might view some of the methods that we want to operate on a stack with. before bringing this into a class, let's just sort of think about how I might do it. If I already just used S as a list and I wanted to define some functions where I had my stack and I had an element I wanted to push onto the stack. So I could define a function, push s comma x, where all I do is I take s and I make it equal to s where I've appended x, and then I return s. Pretty simple. Alternatively, for another method, I can also pop an element off my stack. Now popping, I don't get to specify. There's only just to pop, and whatever is on top of the stack comes off. First, I need to handle a base case. In case my stack is height 0, there's nothing there. So I just need to say that this is an empty stack. Else, I want to remove the last element of my list. And here I'm using some slick notation where I take square brackets -1, where it knows to sort of step in 1 from the end. Wherever that end is indexed using maybe length is the length index. All right, so here we have what happens to our stack once we want to remove this entry. And notice here we're using this built-in method for lists called remove. All right. Of course, we have a more sophisticated way of thinking about these methods, and that's using object-oriented programming. Specifically, we're going to go ahead and create the notion of a stack class. And the specifics of the stack class is going to be something that's initialized so that it looks like an empty list. And then I can add or push things onto the stack, or I can pop them off. And perhaps there's some other things I want to do. Like I want to see if my stack is empty. Or maybe I would like to peek and see what was the last item inserted or pushed onto the stack. Finally, we might want a way to view all the items in our stack. We could write a method called view, or we could use the subject we just introduced where we write what the str method does so that when I go to print a stack, it gives me a way of visually displaying the contents of the stack. All right, let's do that now. All right, so here I'm going to go ahead and use a little bit of trivia I introduced when I talked about inheritance, which is namely that in Python, every class is a subclass of the object class because everything in Python is an object. So I'm going to witness that using the fact stack and then parentheses, whatever superclass I'm inheriting things from. In this class, it's just object. However, I could have just as well not included object. That's basically going to be assumed by Python. All right, so here I have my init method. My init method doesn't take in any arguments, just takes in self. And again, self is going to be whatever variable name we use to create my stack. And then it initializes an empty list. We know that because it uses these square brackets. Okay, so suppose you want to push something onto my list. Well, I can take self.items. This is the items of my stack, which is secretly under the hood stored as a list. And I append that item. I can also pop. And here I can actually use the built-in method for lists called pop. But here I am applying it to this list object, which was only created once I initialized my stack class. That's self.items. This is the underlying data type, may I even say data structure, that is actually representing my queue, or sorry, my stack. Okay. Then I have my notion of is empty. And this just does a comparison operator that's well defined for lists, and asks, is my list of items actually equal to the empty list? And if this returns true, this statement is going to return true, or this method is going to return true. And then finally, I have my peek operator, which first asks, if this is empty, then I'm going to return if empty is false, then I'm going to return this last item in my stack. That's done by this -1. And then finally, instead of writing a view method, I'm going to write my str method, which just tells me what to do and how to print my string. So I'm going to do something a little different here. Again, since the underlying representation of my stack is as a list, I'm going to step through my list and create a string, which I call my return string. And for every item in my list of items, up until the next to last item, I'm going to append the stringification. That's just my way of saying put str in front of whatever self.items in the ith index is. And then I'm going to add a comma so that I'm separating each of the elements in my stack using commas, except for the very last item, because I don't want to have this awkward hanging comma at the end. So I only step through up until the next to the last index. And then I finally append just my last item. I could have also written this as just -1 and dropped the length, because Python knows what it's doing there. Now, instead of wrapping all this string in square brackets, which is how we think of lists, I'm going to put on either side of this string a hashtag on the left end and an @ sign on the right end, which indicates that my stack, the place where I'm pushing and popping, is located by the @ symbol. All right, so let's bring this into memory. All right, so I'm going to call s, create an instance of my stack class. I'm going to push A, I'm going to push B, and I'm going to push C, and then I'm going to print S. So look, we've now created what really you could think of as an abstract data type. This is the stack data type. And the only difference between some of the data types we've already encountered, such as a tuple or a dictionary or a set, is that instead of using round brackets or curly brackets, they now use a hashtag and an @ sign. Why not? Whoever decided we need to use either square brackets or round brackets or curly brackets? It's just a convention. And so I'm now specifying a new convention where my stack data type is going to have entries separated by commas, and it's going to be demarcated on the left and right by a hashtag and by the @ symbol. Okay, so one of the reasons why we do like to think of stacks as data structures is that it's a very useful way of thinking. And perhaps that's really the best definition of a data structure, is it's a way of thinking to solve a computational problem. Here I'm going to introduce a sort of toy problem called the parentheses problem, which takes in the sort of characters that we're used to thinking about in these sort of sets and dictionaries, and also in our lists and tuple data structures, or data types, meaning I know what happens when I have round brackets, curly brackets, and square brackets. And I would imagine that perhaps I'm handed a whole sequence of these, and I want to know, are these all matched like for like? Meaning, whenever I have a round bracket, even if there's some other material in the middle, is that eventually correctly paired with another round bracket? So let's go ahead and say that a string of left or right facing, I should say these are right facing, left facing, round brackets or curly braces or square brackets. Let's say a string of these characters is called valid if open brackets must be closed by the same type of brackets, and then they also must be closed in the correct order. All right, it's probably best to just look at a few examples so you know what I mean. For example, if I have my square brackets and then my round brackets, and then on the outside, my curly brackets, that string is valid because for every type of delimiter here, there's another one of the other opposite type. And moreover, they're sort of sandwiched in the correct order. Now, by contrast, we would not be happy with this because we'd have a left square bracket somehow paired or sitting next to a right round bracket. That's just not right. So let's see one more example of what's considered unacceptable. Well, this is one here too. Now, again, I could actually have placed this square brackets, let's say, in between this round and this curly, and that would still technically be okay, because as I go to pair off my parentheses, like for like, then I collapse down eventually to an empty string. All right, let's try to see how we might do this. So the basic idea is that I assume I'm given a string populated by these sort of left brackets of various types, curly, round, or square, and also in my string I have right, curly, round, and square brackets. And so what I'm going to do is I'm going to imagine I parse my string from left to right, and whenever I hit, meaning I encounter one of these left-facing brackets or left brackets, I go ahead and put it on the stack. And then once we encounter a right bracket, I immediately need to ask the question of, does this pair with the last thing I put on my stack? Meaning if I were to pop that last item off my stack, would I get a valid match? So let's go ahead and see how we do this in code. Don't have an unbalanced pair. Must be close. Have to be in this. All right. So there are going to be some other ways we could check to determine whether or not our parentheses are paired or not. And part of that's just going to be length and counting numbers. But let's see how the stack data structure helps us solve this problem. Okay. So I could put this all inside of a class and somehow talk about maybe a subclass of a collection of brackets. But for now, let's just go ahead and write some of the functions and make use of the data structure of a stack that we just defined. Okay, so the first function we're interested in is a match. So what happens here is we're going to imagine that we're comparing just two objects, two elements of a string, A and B. Well, if A is a left square bracket and B is a right square bracket, then that is a true good match. Similarly, if this is a curly bracket and that's a curly bracket of the opposite direction, that's going to give true. And if this is a round and that's a round, then this will also be true. In all other cases, we consider this not to be a match. All right, so now we get into the function, is Paren balanced? So imagine I take in my Paren string. This is my string of parentheses or brackets. I'm going to go ahead and create an instance of my stack class. I call this little s. And I'm going to set this to be true. Because assuming I write this function correctly and I can properly pop off and pair things correctly, I should ideally end up with an empty stack whose natural status as far as being balanced is true, because an empty stack is automatically, or I should say, vacuously balanced. If there's nothing left to be balanced, then it is balanced. Okay, so I'm going to initialize my index counter at 0 and perform a while loop. So while the index is less than the length of my string of parentheses, brackets, and the is balanced condition is true, then I'm going to first extract the parentheses or whatever bracket exists at the index of my Paren string. And if Paren is in, so meaning if it is a left facing bracket or a left bracket, meaning left or left round bracket, a left curly or a left square, then I'm going to push that onto my stack Paren, my stack S. And that I'm going to push specifically that value, Paren, onto my stack S. Else, I'm going to go through and ask, so let's assume I've got nothing in my, my stack. So if this is empty, then I'm assuming that I'm at an index of my string and I have nothing to pair it with. So let's just make sure we understand that. So what I first did is I took the character that exists at the index in parent string. I asked, is it a left bracket? If it is, then I push it. So now I'm assuming it's not a left bracket. And in particular, I'm assuming it is something, a right bracket of some type. Now, unfortunately, if my stack's empty, then there's nothing to compare it with. So if S is empty, then I'm going to automatically set my isBalanced thing, my index isBalanced variable to be false. However, if it's not empty, meaning there's something there, then what I'm going to do is take a look at the top of my stack. I'm going to call that top, which comes from popping off whatever's on my stack. And then I ask, is this a match between top and Paren? If it's not a match, then again, I'm going to set my balance to be false. And then I'm going to step through, again, this is inside a while loop, so I need to increase my incrementing variable. And eventually this while loop runs through its entire string, parent string. And then finally, as long as my stack is empty and isBalanced is still true after passing through this while loop, I'm going to return true. Otherwise, I return false. So let's see this work on a couple candidate strings. All right, so that last one happened to be balanced, but let's ask about this first one. So intuitively, this is not going to be balanced, but let's go ahead and make it a little more interesting. So here I've got left bracket, right bracket, but when I go to compare, I can pop off here and I'll get a match. But then when I go through and I add this one on and then encounter this, it's going to ask, does this match that? In that case, it doesn't. So let's make sure this returns false. All right, indeed it does. So our isParenBalance function is working, or at least it is working in this example. Now, what about this guy? Here I have some square brackets that are already well matched, but then I've got some round, close a round, I open a curly, I close the curly, throw in another round, I open a square, I close the square, and then I throw in another round. Is this expression a balanced string of brackets and parentheses? According to my function, it is. And again, I was able to solve this using my stack data structure. Okay, so this basically brings us to the end of the lecture. So as a quick reminder, queues are different from stacks. In particular, we push items really onto the back of the list. It means if you've just shown up at the food court and there's a line, you have to stand at the back of the line. It's just how civilized society works. This is what's also called a first in, first out. Be the first one to get in the line, and you're going to be the first one to get your food and you get out of there. And this is an example of something that happens all the time. You go to the post office or bank or the food court. Now, in contrast to the push and pop operators of a stack, we're going to use the operations for a queue called InQueue and DQueue. These are essentially our insertion and removal operators. But again, they can only be InQueued and DQueued in particular locations. So the problems for lecture 8 are going to ask for you to go ahead and try to create a queue class. So as a reminder, we should have an InQueue method, a DQueue method, a front method, which returns the first item of the queue, and a rear, which returns the last item of the queue. IsEmpty should also check to see if your queue is empty or not. And then this should not say implement, it should say print. Let's write a new str method for our queue class. So that'll be the first question. You can do that in however method you like. Again, not meaning to use method in the computer science sense. But you should think about what sort of data types you would use to implement the queue data structure. You probably want to use a list because that's something we're familiar with operating with. However, let's go ahead and try to stretch our thinking a little bit more. So one of the beautiful things in Python is, in any computer science language, is you have to pick some primitive data type, and then you want to build other data types and data structures using that primitive data type. So conceivably, you can make a stack your fundamental object. And so you could try to ask, how would I write a queue using a stack, or maybe two stacks? So in this second question, we're going to ask, can we create a class stack that instead uses queues? And so let's go ahead and try to make the objects and attributes we already made for our stack class, but now we assume we've implemented the queue data structure. There are some further details in the specification, which I'll leave for you to read. I look forward to seeing you in class.